Hi, hello everyone. Can you hear me?
Yes, I can hear you.
Yes, yes.
Yeah, yes.
Oh, thank you for your reply. I also will make a record. So, if Sam, if you want to see the video, you can see it after you back in your house. So, does does anyone preview the lecture too?
Yeah, I did it. Okay.
Okay, so if you don't preview the lecture two, that it's okay. I will make some just key point to remind you, because for this part of the optics, I think that many of you already know the concept. And here in our this this course, and we in the front part of the geometry optics, we just make a quickly introduction and some recommendation for you. So, and some deeply concept that may be different with you have learned before. So, uh, so let us start. Is okay? And if you have any problem, and you also can let me know. So I will quickly go through this part of the lecture two. For the semiconductor optics, in this semester, I will discussion the geometry optics in the formal part, and following, maybe after the midterm or before the midterm, we will go through to the physics optics. So how to distinguish these two different phenomena of the optics? We say sometimes the you can use the particle to explain particle behavior to explain the phenomena of the optics, and or sometimes you need to use the wave behavior to explain it. So we say that if the dimension is more larger than the wavelength, then you need to use the geometry to explain this phenomena is more easy. And if the dimension, for example, when we see that the light goes through a door, and the dimension of the door is very large, larger than its wavelength. So it is probably using the particle behavior to explain the reflection, or the refraction, or some phenomena will be using the particle behavior, will be easy for this. But when the dimension close to its wavelength, such as the slits, or we say some interference phenomena, because of the slits or the hole, its dimension is very small and close to the wavelength. So in that situation, you will find that the wave behavior is more important than the particle, and even it also can use the wave behavior to explain that phenomena will be easy. For example, the diffraction or the interference, such as that. But if the dimension is much smaller than your wavelength, then you know that the particle behavior will become more important. Seems some phenomena such as the optical electronics effect that will happen when the light or when the EM wave incident to a material in the surface, and the frequency will determine the electronics will have enough energy to overcome the work function or not. Also, okay, so in that kind of the situation, it seems that the particle behavior is more important than the wavelength. Okay, so that is already related to the atomic scale. So the dimension is much smaller than the wavelength. Okay, so that is back to the geometric optics phenomena. In this book, you will see in our textbook, you will see that actually in this book, the author he don't separate the geometry and the physical optics not so clear, but in some of the books, they will separate to geometry part, and another will separate. Another part is physics parts. Because that you know that for the Huygens, he used the wavelength or the wave behavior to explain the situation of the optics. But in most of the case, he also used the geometric to help him to explain the situation. But so in this book, the author seems that he also can explain the situation using the waveform. Okay, so in following contents, you also can see that the author using the wavelength form to explain the situation, although we will talking about the geometry part first. Okay, so so sometimes I will jump some section of the more physical optics relation. Okay, and then we will back to discussion this part after the midterm. Okay. Okay, so first, if you have the textbook, or you can borrow it from the library, or sometimes someone maybe find in the internet, or that depends on you. But I think that you have better have an textbook on your hand. Then you can easily to check the contents of what we discussed, and also the problem. I will send you some problems after every chapter. So that is your homework. So most of the problem will from the textbook, but a small part will from other books. Okay. Okay, so that you can check it. And okay, first we will mention that the very important property of the optics, and most of you already know that the refraction. Okay, when the light refraction, we have learned this property before. And we know that when the light impinging some interface, and he will reflect back. So this property is a refraction of the light. And we also know that the incident angle will equal to the refraction angle. So here we just make a clearly definition of the refraction. We say that when a beam of light strikes a jointing discontinuity interface, some light is always scattered backward, and we call this phenomena refraction. So the important is when the light meet a discontinuity interface. Okay, so in our previous learning, that maybe we just know that when the light hits some interface, but what kind of the interface? Here we say it is a discontinuity interface. The discontinuity interface means that the material is different. For example, when the light from the air and the incident impinging on the water surface, so the air and the water interface is a discontinuity interface. And here we also make some spatial identity or spatial definition of the refraction to show this kind of the refraction is from the what kind of the material, such as sometimes we will from the larger the material with larger index, refract index, or from the smaller refractive index. Okay, so this here make the spatial definition or the detailed definition of the internal and the external refraction, just to separate this kind of the refraction is from the interface, from the reflective material from high to low or low to high. Oh, sorry. Okay, such as that. So you can see the figure here show that when a light beam propagates through a dense homogeneous medium, such as the glass, this figure show, and the figure B show when the block of glass is cut and the parted. So this is one glass, and this is another glass. So the middle one is the air. So the light is reflected backward to at two new interface. So here mentioned that when the light emitted on the mid discontinuity interface here, and another is here, they will both have the reflect backward light at these two new interface. But for the beam one is this one, and this one. So this one you can see that the light is from the air incident in the glass. So the refraction light happened, and this kind of the refraction of the beam one, that we called it as the externally reflected. So that means that when your light is from the small n small to n large to get the refraction light, and this light we will call it an externally reflection. Okay, so in another word, we say that the beam 2 is from the glass to the air. So the beam 2 is when the light impinging in the interface of from the light travel from the n larger to n small, and he get beam 2 refraction. And this refraction that we call it as internal reflected. Okay, why they separate this kind of different situation? They just want to clarify that the light is reflected by the n small or reflected by the n large than the original medium, and some different situation will happen in these two different situations. Okay, so this one show the internal and the external reflection in the light. And here you also can see that the figure using the waveform to show the incident and the reflected light. Here you can see the flat one means a wavefront. What is the wavefront? The wavefront is combine or connect with the same phase. Okay, when the phase is the same, and then construct the wavefront. For example, we have the wave such as this. Okay, all of the heights of the wave, they can connect to construct to the wavefront here. So for the left side, this is a cross-section view of the wavefront. Then you will see the black one and the white one. If the black one means the top of the wave, then the white one will means the bottom position of the wave. Okay, and so this is the same wavefront. And the direction of light traveled will triangle to the wavefront. Okay, so here the Huygens try to use the wavefront wave situation to explain the load of reflection, and later we will see he can use this scrap to explain the load of the reflection, but how it explained the load of the reflection. He also using the geometry science. So actually you will see he tried to explain it using this triangular is the same with this one. So the incident angle will equal to the reflection angle. And what is the incident angle and what is the reflection angle? Okay, he tried to using this kind of although this was constructed by the wave structure, but he finally using the geometry to help him to explain the incident angle is equal to the reflection angle. And what is the incident angle? We know we both know that we all know that we can see this structure. Here you can see that we have the surface normal. The surface normal is vertical to the interface. The blue plane is the interface. So the incident light will react to the surface normal, have a incident angle, a theta 1, a theta I, and the reflection light will react to the surface normal, have a this word is wrong, refractive angle, a refractive angle theta r, and the theta I will equal to theta r. So this is the law of the reflection, but this is we all know when we are very young. Okay? So even in our childhood period, we all know this. But now we need to have a more detail or more clearly to definition this situation. For example, that we both know that the incident angle will equal to the refraction angle. But do you know where will be the refracted ray happen? Okay, let me change the can you see me? Okay, so you know that this is an interface, and the incident light is from this direction, but where is the refraction light, refracted light? The light incident here, and the reflect light maybe reflect to this direction, or reflect to this direction, or reflect to this direction, right? All of the direction that we can make a refractive angle with the normal. So this will happen because that in our world we have the three-dimensional, but in the PowerPoint that you see here, maybe it is a plane. So in the plane, we can easy to know where will be the refracted lights, refracted rate. But it can actually in the 3D dimensional in our space, the world space, that you are hardly to we need to more clearly to definition the refractive law of the refraction. So beside the incident angle equal to the refraction angle, then we must add another condition, such as this figure show. This figure shows, say, the all of the incident ray, and the refracted ray, and the refracted ray, and the surface normal line will exist in the same plane. This plane is what we call it as the plane of incident. So the incident ray and the refraction ray and the refraction ray and the surface normal all exist on the plane of incident. And where is the plane of incident? The plane of the incident will vertical to the interface. Okay, so this that will help us more clearly definition of the law of reflection, and also the same as the rate of the refracted ray. So later we will see.
Professor, so
Yes.
your theta r is the reflected or refracted?
Sorry.
The in the figure.
Yeah. The figure, the type it is wrong. This
typo,
is
right?
Yes, typo. The upper one is reflect.
Oh, okay.
Sorry.
So that make me confused.
Sorry.
Yeah. Thank you, Professor.
Reflected. Okay. So so someone will make a misunderstand of the plane of incident. Actually, the plane of incident, not the interface. So is that understand? The interface is the discontinuity of the material. So the light meet the interface, then will the reflection and the refraction will happen. But all of the incident light and the refracted ray will exist in the same plane, and this plane that we call it as the incident plane. And the incident plane will vertical to the interface. Okay, so that we can understand that the incident lights, the refracted light will happen in this direction, not this direction, or not this direction. Okay. Is that okay?
Yes.
Thank you very much for reply. Okay. So following, we will say that all the phenomena when the light impinging in the interface should be followed of the law of reflection. So in our imagination that we seen that all of light will have the parallel light, but sometimes you will see that maybe light reflected in different direction. So that's because of the surface of the interface. If the surface of the interface is very smooth and very flat, and you will see this kind of the situation that we call it as a specular refraction. So in this kind of the case, that is it. The example is you see the mirror. You see the mirror that you can easily to see the clearly image from the mirror, that this is a specular refraction. But for the another case is that if the surface of the interface is not so flat, is rough, such as this figure show, then the light will refract in different direction. But you must notice that in this part, in every point when the light impinging in that surface, actually that surface is also follow the law of refraction. Means that the refraction angle will equal to the incident angle, but the surface is so rough, so the totally result seems the light incident in different way. But in the impinging surface, that should be follow the law of the reflection. And when this kind of the situation happened, you will see that the light not just incident in the same direction. So you will see the blur here, or not clear image. So it is very easy when you are go to a lake if there is no wind, and you will easy to see the clearly image from the nearby house or the ship or such as that. But you are very clear to see. But if there is wind, then you will see the ripple in the surface of the lake, and the figure, the image will become not so clear. Okay, and here is another application of the law of refraction. You know that when they detected is there any flight or not, they using the radio wave to emit a radio wave to the aircraft, and so they will directly the light will directly reflect back of the aircraft. So the radio the station can detect them. But if we change the surface by tilt angle, then the radio wave will reflect to another direction that they can not easy to get a reflect back signal of the microwave, so they won't detect the aircraft. Okay, so this kind of the aircraft using very this kind of aircraft with a flat tilted plane, so you can see that the surface is not so very flat and not so very smooth, because they construct it by many tilted planes, and they can avoid theta I equals theta R. They not equal to 0. Okay, avoid equal to 0, because the theta I is equal to theta R. If equal to 0, then the light will directly send back and be detected the light. Okay, so this is a kind of the aircraft structure. Okay, so also let's go down the refraction, and this also using the waveform to construct the refraction, and you can see that the when we know that the if the black part is the top of the wave, and this is another type of the wave. So this is the wavelength of the light of the wave, and you can see when the light travel to another material, a transmit medium, the wavelength maybe will change, because the refractive index is different with the original incident one. So the velocity actually is the velocity will change. Okay, so this is the Descartes arrangement of the deriving the law of refraction. So, and he also know there have some connection with the theta I and the theta T. Okay. Okay, so that is back to this figure. So also the same with the refracted ray. We know that actually we know the law of refraction is the sine theta I divided by sine theta T will equal to a constant. And the sine theta T, the theta T is a refracted ray, a refracted angle. Okay, so it is a refracted ray relate to the surface normal line. Okay, so beside this one, if we want to describe a refraction, law of refraction, we still need to not only need to say that the Ni multiple theta I will equal to Nt multiple theta T, and we also need to clarify that the incident rate and the refracted rate and the surface normal are light on the plane of the incident. Okay. It's the same with the law of reflection. Okay, so this is using the uh, using the experiment set up to see the refraction situation. And this is the image of a pen sees through a thick block of the clear plastics. Because of the refraction, light the way to reversion light, so it is seems that the the pen is broken. Okay. Because the light is not directly move to the same direction. It is a little okay. It is a little reflected, not in the same direction of the incident light. It is bending. Okay, here shows this figure just show that the okay, this big figure just show that when the light incident to a dense material, the refract index is larger than the original one, or incident to a not so dense material, what the light will bend it to which direction. So for the A figure, you see that this is a from light from the air to the glass. So the Nt is larger than the Ni. Okay, so from the law of the refraction, we always say it is a Snell's law. We know that the Ni sine theta I equal to Nt sine theta T. So if your Nt is large, this is large, and the Ni is small, to make the equation equal equation, your theta I must be large and the theta T must be small, right? Because of the equation. So you will see the Ni here, theta I is large than the theta T. And also, if light in the figure B, the light is incident to not so dense material, the incident light, the incident material is denser than the refracting material. So here you will see that this is Ni larger than the Nt. So you will have the larger incident, larger transmitted angle with the this is theta T, larger than theta I. Okay, such as that. So someone will say in another words, they will say that light always bend toward to the more dense material. So you see figure 1, the glass is denser than the air, means that the refract index is larger than the glass is larger than the air. So the light bend toward to the more dense material. And compare of the B, okay, so this one is more denser. So the light will bend to the more dense material. So here is a transmitted light. The transmitted light is bent toward to the more dense material. Okay, this figure is an interesting figure that a beam of the light enter from bottom moving toward. So the light from this one. Okay, and here are two Polexco block widely separate in air. So in the middle one is air. So when the line incident in the Polexco Polexco glass, so in every interface you will see the reflection light and the reflected light and the refract and the transmission lights here in every interface. Okay, so you will see many lights here, but when they making the air gap thin, two of the reflective beam will overlap to form the bright middle beam travel to the right. So you can see here the light is number of the light smaller than this one. So see when by replacing the air beam with with the has the oil in the interface here. Feel the oil in the interface between the block and the sunlight will vanish as the reflective beam. So you will see just two beam here. Okay, so that will be first reflected this one and another transmit by this one and reflected. Okay, so also if at it behavior just like a single solid block, it means that if we put the material in the interface of these two blocks, and the material is the refract index is similar to this block, then the interface will vanish. So the behavior will work with the just one block here. Okay, this is a very easy example to calculate uh, the refraction angle, or we say the transmission angle in the glass. So a few points that I will mention is we need to know the incident angle. So you can see here, this impinging angle is respect to the normal. So that's mean this is an incident angle. And some question will say the angle is respect to the interface. This is interface. So if you want to, if we say that the angle is respect to the interface, for example, 60 degree, then what is the incident angle? The incident angle should be 30 degrees. Okay, so here we need to clarify that what is the incident angle. And here shows another words of the reflective index of the refraction. What is the reflective index of the refraction? That means the NTI. NTI is the NT divided by NI. Okay, so this definition is the reflective index. Okay, some book will have this kind of definition, but some book will not have this one. Okay. Okay, so here the first question is to determine the reflective index of the refraction. So we need to calculate the NT divided by NI. Get this word. Get this answer. And the question of the B is what is the beam transmission angle in the glass? So you can using the Snell's law to calculate the transmission angle. Okay, another example here to show the phenomena of the actually the optical fiber is also using this property to transfer the light from to can transfer the light to very long place, okay, to very far place, help us to transmit the image or the any data sent to a very long distance. Because of the ray can continue to transfer in the optical fiber or in such kind of the parallel block such as this. So here use a very simple concept. Ask us to calculate the many angle of the theta 1 till the theta a to calculate. So for the first interface here, when the light impinging on a block of the glass, so this is a glass, this is air. So when the light impinging this interface, there will the reflection of the light happened and the transmission of light happened. Okay, so using the Snell's law, we can calculate the theta 2, and using the reflection law of the reflection, then we can calculate the theta 1. Theta 1 is equal to the incident angle, and the theta 2 is the using the law of the Snell's law here. So we can get the theta 2, and for the theta 3, okay, for the theta 3, because this block is this two surface is parallel, so it and this is the normal line of the interface. So it construct a triangle, the this kind of a triangle here. So we know the theta 2 plus theta 3 will have a normal angle. So we can easily to calculate the theta 3, and for the theta 4, it need to follow the law of reflection. Okay, so theta 3 is equal to theta 4. Okay, so with this method that we can easily to calculate every theta every angle here. Okay, so but why the light will continue to travel in such kind of the black or in such kind of the glass? Later we will talking about this. This is the total internal refraction. Okay, here just shows the Huygens principle, and quickly to say that the Huygens using the same concept of the point source of the water. When the stone drop in the water, they will the point source will happen. Then they will rise the wave of the water wave. Okay, so he said he's thinking that it is the same situation with the light. So the light will emit it in all direction and create a series of crystal in the tops here. And here says that the light will traveling emit in all direction. And here shows that the light rate. What is the light rate? The light rate means a line will perpendicular to the wavefront, and this is a wavefront. And we already explained the wavefront. It actually is a surface of the constant phase. So construct by the same phase, okay, to form the wavefront. Okay, and this is I can say how to form the next new wavefront. He said that every point in the original wavefront can be the wave source. Okay, and every wave source will emit a small wave. Then we connect the tangents to the wavelet. Then we will construct the new waveform. Okay, so what is the diameter of the wavelet? Okay, that will relate to your lambda wavelet. Okay, or some in the same material that you can say in after a certain the path of the after a certain time traveled, so you can construct this wavelength. Okay, and using the same wavelength, they will uh they will exist or they will happen the new wavelet. Then make a tangent to the wavelet. You will get the new wavefront. Okay, so if the new wavefront is a plane, okay, that we will call it as the plane wave, and the new wavefront is still, and also the new wavefront is still a plane, as long as the dimension of wavefront are larger than lambda. Okay, so here shows some terminology. We will heard that the spherical wave or plane wave, such as that will depend on the structure of the surface. So what we call the surface spherical wave, that means that the wavefront are spherical. And so for the plane wave, that means the wavefront are planes. Okay, so and the ray means the direction of optical propagation, the optical direction of the propagation, and that should be perpendicular to the wavefront. Okay, this is a wavefront. Okay, and this one is the rays, optical rays. That means propagation direction. Okay, here we mentioned that the hero's principle. This is the hero of Alexandria city. He said that the path taken by light in going from one point A to the point B, they should be using the shortest possible one. Okay, so he means when the light meet impinging in the interface and he will reflection. So but the reflection path or reflection point must show the uh, using the to be go from A reflect by the interface so go to the B should be what?
Professor, can you repeat
Go
the one you just say because the connection was lost?
Makes up the connection. Hmm? Sorry, I will make a refresh connection. I don't know why what I see is the okay, the internet is okay, but it say it is not okay. Okay. Oh, okay, here. Okay, we say that when the light travel from the A point by reflected by the interface here, and then go to the point B, they have many ways. They have many ways that they can travel. But why he choose the yellow ray? Why he choose the yellow ray? Okay, so we can also easily using the geometry methods to prove that why he go through point O and to go using the yellow line ring. Okay, so I think we are very easy to prove this that we can set the normal line to this interface and set the AR. Here the AR equal to A plan R. So the A O plan will equal to A plan O plan, and the AO9 will equal to the A plan O. So for using the geometry concept that we know the compared to this triangle, we know that the A plan O plan plus B O plan always larger than A plan B. Okay, the A prime B actually will be the A prime O plus the BO, right? Okay, so using this, we can prove that why the light, when he refracted by this interface, should be choose the AOB this way. Okay, this is a hero's principle, but he tell us that the lights will go using the shortest the shortest way possible one, but actually the the famous will prove that not take the shortest way. They should be take the way by spend shortest time. Okay, later we will see. Okay, so and also we know that the speed will change when light travel in different material, different mediums. So we make a concept of the refract index. The refract index actually we using the definition of the C divided by V. The V is the speed when light travel in the material in the medium. So we know that the light travel in the vacuum space will be different in the any medium another medium. Okay, so we will have the refract index of the material. And here we show that the Fermat principle, actually the Fermat proposed a principle of least time encompassing both reflection and refraction. So maybe in the consider the hero's principle. If the hero principle is right, it is just can use in the reflection. Okay, reflection, but cannot application of the refraction, because we know that when the light transmits in the material, it is not go directly through the same direction of the incident light. Okay, so it is bending. So uh, the the uh, the shortest way is not cannot used in the refraction. So the Fermat proposed another theory that both reflection and the refraction will using the least time. Okay, so the actual path both between of 2 points taken by the beam of light is the one is the one that is traveled in the least time. Okay, this is a very important concept. Okay, so maybe we will see this question in the midterm. Maybe I will ask you what is the Fermat's principle. So you need to write, you need to tell me this one. Okay, this is what Fermat to prove that his concept is correct. He using the easy proof to also the geometric method to prove it, and he need to show that this is this time. So just using the dt divided by dx is 0, then we can know what is the limit value of the t. And when this concept is correct, he solved this equation that he can get the Snell's law. Okay, he can get a SNES node, so that will that prove that his concept using the shortest time is correct. Okay, so but we won't prove this here. It is on your textbook, so you can take time to, if you are interested of this, you can take time to see how he proved this concept. Okay, now we want to go through to the optical path length. What is the optical path length? We can see that when the light transmit from the S and crossing many different material to the P. Okay, so we know that the transit time from S to P will have the distance divided by the velocity. When it travel in different different material, the velocity of the light will be different. So when the light travel in the first median, the spend time will be S1 divided by V1. Travel to the second material, that will be S2 divided by V2, such as that. So we can write that actually the V1 is equal to the V1 will equal to C divided by refract index, right? So when this one is the C divided by index N1, and this also C divided by N2. Okay, so now we can, that every term has the C, so C can take out. And the left one will become the NISI, and then we plus the every NISI together. Okay, so when you see this equation, it seems that if the light travel using the speed of the this C, and the distance, this is velocity. Okay, so the distance will become this one. So what it means, that means that when I was the light, and when I traveled in this material, I seems that I using the speed of the light C to travel. I don't know. I don't seem so. I don't seem that I change out my my velocity. I also using the C speed to travel in this material, but it seems the distance changed. It seems the distance changed. The distance is already changed to refract index multiple S. Okay, so this one that we called it as the optical path length. Optical path length. So you can imagine that if you say the light still using the C to travel in the material, the path seems to be changed to the N multiple S. Okay, so this is what we call it as the optical path length. It also can write by the integer form, such as this. Okay, so the time, the spin time will be the optical path length divided by the speed of light, c. This is what we say the optical effect. Some optical effects using the refraction phenomena of light. Looming or the mirage also using this style. You can see that actually if the sun is go down to below the sea level, you are hard to see it, but we can easy to see it. But because the refractedness of the atmosphere was changed in every level, a different level, the refractedness will different. So the light will go through by in this way that you can see here. And but the final one image to your the light image to your eyes is this direction. But you will see that you don't know that the light is already bending. You see that the light go through directional directional go through. The direction is go through. Okay, so you don't think that the light expanding. Your mind won't believe that, and it will not calculate by for you that how much it bending. So when we see the light, we always seems that we always see that the light is directly goes through to your eyes. So you will see the light is go from this direction. Okay, that image also can this phenomena also can explain why we see the pen or the chopstick bending in the water. And this is a mirage when the tree is here. But we know that if the atmosphere of the upper one and the bottom one, the temperature is different, then it also will change the refractedness of the air. So when the upper one is a cool air and the bottom one is a hot air, the light from the tree will go through such as this kind. Because the refractedness is changed, so the light will a little bending. So to another direction. So when the light go to your eyes in this direction, then you will seems that the light go here direct to your eye. Okay, so you will see an image here, such as this figure show. Okay, such as this one. Okay, the situation also seems to in the sound. The sound also can show this kind of the situation. This figure show the paddle mirage. Okay, can be understood via wave. The situation also happened in the place that the upper air the refractedness of the upper air is different with the bottom air. So such as this one, you can see that the upper one is the cold air and the bottom one is a warm air close to the palm. So if you yield in this position, but the sound seems cannot travel to the other side here. But when the situation is changed, that the upper is a warm, have the warm air, and the down have the cold air, then you will sound also can a little bending, so you can easily to send your sound to another part. Okay, and we already introduced the law of the reflection and the law of the refraction, two kinds of the property of the optical light. And the third one is the principle of the reversibility. The reversibility tell us that what the light from A point to the B point, what kind of the route it takes, then reverse, and you also will take the same route. So for example, you can see this picture. This is a elliptical surface of the elliptical structure surface, and when the light go emitted to the Q point and reflected to another P point. This is two focus of the structure, and if the light go from the P point, they also will reflect it back to the S point. So this means the reversibility tell us if the source is here and the P point is image, then we put the source in the P, then the image should be in the S, because the light have the reversibility, but the property. Okay, this is a reflection by plane surface tell us that when every reflection reversion happened, then the image will change one direction. For example, when we see in the mirror, you know that the left side and the right side of the image were different with us. Okay, so every reflection happen, the image will change one dimension. Okay, so you can see here, the law of reflection tell us that the R, if the R position can be right as the X, Y, Z, when they make a reflection make a reflection here, and the image of the R2 will become X minus Y and then Z. So the one dimension will change. This reflection through the XZ plane. So you can see the right side figure when the R1 position is the XYZ, and then first reflection, the image will change to the minus XYZ, and the second reflection will change one direction. Then the image will become minus X, minus Y, and the Z, and another reflection, then the position will become minus Y, minus X, minus Y, minus Z. Okay, so the following is the total internal reflection. So this kind of the reflection, why we say it is a total internal reflection, that is not because it reflects back to its own material. And it means that this kind of the reflection is happened. This kind of reflection happened in the situation of the internal reflection. So in the beginning of this class, we say, what is the internal reflection? The internal reflection means the light traveled from the n large to n small, right? So this kind of the reflection just will happen when the light travel from the material with n large to material with small reflect index material. Okay, so here we can see that because Snell's law tell us because the N1 is large, the N2 is small, So the theta 1 will be smaller than the theta 2. So you see the theta 1 is smaller than the theta 2. So when we increase the theta 1, the theta 2 will increase, will be also increased. So sometimes in some situation, when the theta 1 incident angle become to a certain angle, then the reflected light will with refraction light will be have a normal refraction angle. The theta t will become 90 degree. Okay, so when the incident angle, in this kind of a situation, the incident angle will be called as the critical angle. So when the incident angle is larger than the critical angle, theta 1, larger than the theta c, then total all of the light will reflect back to its own material, such as this situation happened. So this is what we call it as the total internal reflection. Okay, so you know that this kind of situation just can happen under the incident light material travel, the light travel from the large the reflected material to the small refractive index material. Okay, so here we can see the measurement of here. This 4% shows that if this is a glass and this is the air. Okay, we all know that the transmittance of the glass is large, so only 4% will reflect back when the incident angle is 0. So, but if we increase the incident angle, and you will see the reflection angle will increase. But when the incident angle will equal to the 42 degrees C, then you will see the transmission angle will become 90 degree. But this is a reflected angle, reflected light. But in this case, when we measure the power of the reflected light, we will see actually already reach 100% of the reflection light. This 100% is compared with the incident light. So that means that when the light emitted with the critical angle, and we can get 100% of the power of the reflect light. Okay, so and also when the incident angle larger than the critical angle, so all of the light will reflected, and no transmission lights, normal transmission light. So when we say when will total internal reflection happened, what is the condition? That means you have two conditions. The first one is the light should be traveled from the n large to the n small. So when the light should be traveled from the n large to the n small. Okay, and the incident angle should be large or small, large or equal to the critical angle. Theta C is the critical angle. And this is the incident. Okay, this is very important. Okay, so also may happen in your midterm equation, midterm question. Okay, so here shows that we just need to create a situation that have the n large and the nearby is the n small. And if we send the light into the n large and the incident of the interface here is larger than the critical angle, then we will get the light always travel inside this region. So this is what we see in the formal question. The light travels in the parallel plate or in the optical fiber. Okay, using the principle of the total internal reflection or the situation of the total internal reflection. Okay, is this okay for you? Okay, here shows some example of prism and the total internal reflection using the prism to when they incident the light incident in the surface of the prism, it will happen total the reflection. Okay. And or also this kind of the prism we were using this kind of prism to maybe reverse the image or change the direction of the light. Okay, is there any problem with this part?
Yeah, yes, Professor, I have a question.
Yes, please.
Can you go back to the 6 pictures of the internal reflection?
This one.
47.
This one.
Yes. So I want to know, how do we know that the incident angle is larger than the critical? Because I see F.
Okay.
Yeah.
Okay, sorry. That we know that this Ni also using the Snell's law, how to calculate the critical angle. Ni sine theta I will Nt sine theta t. Okay, so we said that when your transmission angle will equal to 90, then in this kind of situation, the incident angle, we call it as the critical angle. So if this is the glass equal to 1.5, and this is the air equals 1. Okay, so the Ni will be the 1.5. And in this kind of situation, the theta I is critical angle equal to the Nt is 1, and the transmission angle is 90. So this is also equal to 1. Okay, so, and you will get the sine theta c will equal to Ni with Nt, right? Here is the E1 divided by 1.5, and this is 1. This is 1, so you will get this 1. Then the theta c will equal to arcsine. Okay. Then we can count. Yeah, we can calculate the critical angle. Okay, any problem?
No problem.
Thank you. So we will go to another PowerPoint. This PowerPoint that we will say some discussion, some situation of the optics, the optical system. So beginning to discuss the optical system, that we know the image and the source and the image point, the object and the image point. Okay, so when we discussion, we know that if we have some object here, and when the light emit from the object and close to the optical system, for example, the mirror or the lens or the combination of lens or combination of the mirror, such as that, and they will form an image here. Okay, so we know that from the light reversibility property of the light, we know that the object and the image are the conjugate point. That means that every light from the object will go to in the image position. But if we change that the image, the object position is here, then the light will go the same route to the object position. The original object position now will be from the image position. Okay, and also we were using the Fermat's principle to help us to know what kind of the optical system will form the perfect image. Okay, because Fermat's principle tells us the optical path length of every ray passing through eye must be the same. That means every light emit from the from the object past the optical system will reach the image point in the same time. So there must be, the time must be the same. So the optical path length must be the same. So here shows some interface between air and the glass, and should be the hyperbolic interface or ellipsoid interface, because using the Fermat's principle, they can calculate what kind of the surface can form the perfect image. Okay, perfect image means that if your object is points, then your image also will be a point, very, very small points, not the burn one. Okay, so using the they can we don't prove this part. It is shown in the textbook. I just quickly to explain it, that using the Fermat's principle, they can assume that one light through the go to the optical system, maybe this line, and the second line maybe using this line, but they all have the same optical path length, so they can solve the equation to get the actually there exists some certain surface can form the perfect image. On that kind of the surface, we call it as the Cartesian surface. So the Cartesian surface means those surfaces which form perfect image of a point object. Okay, what kind of the surface, a Cartesian surface? For example, ellipsoid and hyperbolic surface. Okay, so when the nt divided by ni larger than 1, there should be using the hyperboloid surface that can form a perfect image. But for the nt divided by ni smaller than 1, that the ellipsoid surface will form the perfect point source, such as this figure shows. So here shows that this is from the hyperboloid, and the C and the D shows the ellipsoidal refracting surface. Okay, can form the perfect image. Okay, so you know that if we using the hyperbolic and the hyperboloidal and the ellipsoidal surface, then we can form perfect image. But I think that you heard the mirror or the lens that we called it as the spherical mirror or spherical lens. Why we using the spherical one? Because you know that to make a lens or the mirror or especially make a lens, they have to using the polish method to make the lens, and to make a spherical lens is more easier than the hyperbolic surface or than the ellipsoidal lens, the surface. So this is why the we will have aberrant image will happen. Okay, so that is why you see some image will torch or will bending in the outside range, because we know that if to form a perfect if to form a perfect image, that we need the ellipsoidal surface. So in the middle one, the curve, the curve of the spherical lens and the ellipsoid, this is a spherical. This is a spherical lens, and this is the ellipsoidal lens. And in the middle one, they will have the same curvature. They will have the same curvature. But far from the middle one, they will have some difference. So that is why if your object is far from the middle side, the image has a little bending of that. Then later we will, in the following chapter, we will discussion of this, because all of what we imaginate is using the small angle small angle imagination. Okay, so here mentioned that if we using the hyperbolic lens to all the ellipsoid lens, then we can have a perfect one, a perfect perfect image points. Okay, so but now we're using the spherical interface to close to the perfect Cartesian surface. Okay, so here we can using the simple method to find out what is the image equation. To find out the image equation, the image equation means that we can estimate if we know where is the object position, and then we know the refract index of the interface, then we can using the equation to find out where should be the image position. Okay, so we know that the close to the middle side of the position of the middle side of the lens, the curvature will be the same with the Cartesian surface. So where we use is the parallel ray approximation. What is the parallel ray approximation? Means that the all the object is in the middle side, close to the optical axis. So what is the parallel axis? Means very close to the optical axis. And the optical axis is actually the middle line of the lens or the surface, or the refractive surface. So now we would like a single surface to provide image for the S, and the S plane is this is the object S, and this is the image position. And this will be true if we place certain restriction on the bundle of the ray collected by the optical system, and then we can use the parallel action ray approximation to find out where is the image position. So now how to using the parallel action ray approximation, that we should be assume the this y is the height. The height is very smaller than the position. So what is that means? That means that all angles are small. All angles are small because the angle is very close to the actual here, and the incident interface of the reflection or refraction is very, very small, and the x also smaller than the S plane and the S. Okay, so here we can make some benefit from the parallel action approximation, because all angles are very small, so the sine alpha will equal to the tangent alpha, and then will equal to the alpha. Okay, so we not because you know that the expansion of the sine alpha can equal to the alpha plus and then we just take the first term. Also the cosine alpha, which just takes 1. And using this approximation, then the Snell's law will become n theta equals n prime theta prime. Okay, and all distance are measured from the vertex. Okay, so here we can quickly see the approximation to find out the image equation of the refracted surface. Okay, so here you show that we sorry. I will use this figure to find out the refraction at the spherical surface. So here you can see that we can draw this one. So the object is on the middle side. This is the optical axis. So the object's here, and the image aligned toward to the surface, the refraction surface, and this is a refraction surface, so the light will transmit it. Okay, and they should be follow as the normal light of the surface will pass the center of the curvature. Okay, so this line, this dashed line means the normal line to the surface here. So this angle will be the incident angle, and this angle will be the transmission angle here. Okay, so using the simple geometric methods, that we can know that the alpha plane will be the outer angle of this triangle. So alpha prime will be equal to phi plus theta 2. Alpha prime equal to this is a theta 2 and plus phi here. Okay, and the alpha 1, we can see this alpha 1, we can see this triangle here. So alpha will equal to theta 1 plus phi here. Okay, so and then we can get using the Snell's law. Snell's law tell us okay, so theta 1 here, theta 1, and this is theta 2. Okay, so and now actually we using the parallel axial estimate. So actually these points should be in here. Should be in here, that will what we assume all the incident angle is very small, right? But we draw the point here to enlarge all the angle that you can see here. So we draw the angle, so we draw a point so high. Actually, the incident point should be here. Then if the incident angle should be here, then you will know that actually the Q is very close to this point, the middle point V. Okay, and so now we can rewrite this equation that alpha will equal to near equal to the sine alpha and the tangent alpha. So the tangent alpha actually, the alpha here, the tangent alpha actually is this S1 H. The H divided by S is the tangent alpha or the sine alpha. Okay, so here alpha we can write H divided by S, and also the phi is this one. Actually the point is even here. Then this distance is actually is the curvature, so it's R. So the phi we can write as H divided by R, and also the alpha plane and the phi, so we can write the equation here. And to manage the H then we can get this equation. Okay, you can get this equation. But when we check another situation of this kind of the situation, okay, so if the light surround here, okay, then we also can find out the equation similar to this one, but the sign will be different. So we will have to make a we will have to make a definition of the sign. Okay, so first is a line is travel left from the right. Make all the line is travel under the left to the right, travel left to the right situation, and to see the positive or negative of the sign. Okay, and the V is the orange, or measurement distance is measured from V. Okay, and the R is a curvature. So if the center of the R, the center of the curvature is positioned to the right of V, then the R is positive. That means that if the line travel from left to right, and if your curvature, your surface is such that this curvature, because the center point here is right in the right of the V. The V is the vertex here. So the R is positive. Okay, and for another one, this one, this is V, and the C is here. So the R is negative. Okay, and the S is the object distance, and is made from the V, and how to know positive or negative? We say that for the real object, the object distance is positive. So that means it's actually an object there, and the light is emitted from the object. Okay, so actually that should be in the left of the V, because the light from the left side. So if your object here, and then that should be real light from the left side to the V. So the distance here will be the positive. But if your object is behind the V, but our light is from left side, so you should not see the real object. Okay, so in this kind of a situation, the position, the distance of the S will be negative. And also the same situation for the image distance. Okay, so if your image is a real image, that should be the image distance will be the positive, and the image, if the virtual image, then that should be the negative one. So when the interface, this is a refraction interface. For the refraction interface, how to form the real image? Your object here, then the light from here should be collect in the right side here. Your light actually real collect in the right side here, then it will form the real image here. So this kind of the image distance, this S-prime, will be positive. So in the reflection or in the transmission situation, the image should be to the right of the vertex, such as this. That will be positive. But if your image is in the left of the V, that your image will be the virtual image. So the image distance will be negative. And for the height of the object or the image, and the positive means the object is high. Okay, so in this situation, the Y is positive. But in this situation, the down, that means that the Y plan or Y will be negative. So the object distance or the image distance is positive or not is related to the real image or real object. Okay, but for the high, positive or negative just mean its direction, it's up or down. Okay, all of this also shown in your textbook. You can see if you want to find the description in your textbook, you also can see page. Okay. Okay, this figure shows a virtual image points such as that. Okay, you can see that this is a parallel line go to image impinging in a surface such as this one, transmission surface. Then after transmit this surface, it will divergence as this one. So in this side of the light actually diverges, but in the backward, it seems to can it seems to be to focus on these points. Okay, but there is no real light focus here. Convergence in this point. No real light convergence in this light. So convergence in this point. So this is a virtual image point here, because the real light already diverges. Just a backward will converge in this point. And this figure showed a virtual object point. It is a little hard to imagine the virtual object point, but after then we see the question, then maybe you can easily know what is the virtual object. Okay, let us back to the reflection at the spherical surface. So we know that from the formal calculation, we got this equation, and if we consider the regulation of the sign regulation, then we can put the rule into this equation. So for the figure here, we know that it actually not from the real image. It is the like backward to form the image here. So this is a virtual image. So the x-plane should be minus. Okay. So if we change minus, okay, and for the r, the curvature sign, the center point of the curvature will be the left side of the v. So this r also will be minus. And if we using the same, we using this method to find out the image equation for this kind of the surface, we will get the equation form of this one. So we want both of them all can use the same equation. So if we using this equation and make the formal rule of the sign, okay, then we can using this equation. Okay, because s-plane is minus, so it will be the same as here, and the r will be minus, also the same with this one. So just using this equation and following the rule of the sign, this rule of the sign, then we can also using this equation to find out where is the image. Okay, and here is using another method to also the parallax ray approximation to find out the lateral magnification. How to count the lateral magnification? We also can using the image here and the figure here, and here we assume that the object here and the object height is h0, and to have a real image here, and the image height is hi. Then what is the lateral magnification? The lateral magnification means the height of the image to divide by the height of the object. Okay, and so using this figure, then we can apply the Snell's law. Snell's law told us because this is a parallel ray approximation, so we're using the n1 theta 1 equal to n2 theta 2, and the theta 1 here will be using the h0 divided by s. Okay, and theta 2 here can using the hi divided by s1. Okay, so we want to calculate the hi divided by h0. Then we can using the equation to find out the hi divided by h0 will be equal to n1 s1 divided by n2 s. Okay, so why we got the minus, the negative sign here, because you know that the real image is inverse, downward. Okay, so we using this sign, the negative sign, to represent that the image is have the different direction with the object. If the object direction is upward, then the image will be downward. Because after the calculation, then this is a minus sign here. So if you when you calculate the lateral magnification, when we got the positive m, that means that the image will be have the same direction with the object. Okay, so following we can using the easy example, this example to check the application of the equation. So here we have a interface of this interface, a transmission interface. Then the object distance is 30 cm. It's positive here, and here has a convex surface. So the structure of the surface is such as this. And the curvature is 5, and the N1 is 1. N1 is 1, N2 is 1.33. And the image position, he want to find out the image position and the lateral magnification. So here we can using the equation to find out the where is the image. And here we want to make sure that the S is positive, because this is a real object, and the R is positive or negative, because the curvature is such as this. This is a convex curvature, and the center of the curvature will be in the right side of the vertex. So the R will be positive. And okay, so we can easily to using this equation to get the position of the image is positive 40 centimeter. That means this is a real image, because the sign is positive, and the position will be the right side of the V. So that should be here. Okay. And in the lateral magnification, we'll be using this equation. So to replace the number inside, then you can get the -1. The m is -1 means the image is inverted relate to the object, because the object is upward, so the image will be downward. Okay, and the number is 1 means same size with the object, because the m will be the h I divided by h o. So if equal 1, then will be the image height of image will be the same with the object image. So using this equation, then you can have a practice one. You can practice this equation, this question to make sure that you know how to using this equation. And another equation, this question is not in your textbook, in other textbook, but it can help us to connect with the secants and the secants. So I using this question here to make sure that you can understand how to application the image equation of the refract surface. Okay, so here we have the secant surface. The secant surface is 10 cm centimeter behind the first surface, and the second spherical surface concave. So we draw it as this one. So for the concave surface, the R is 5 centimeter. Now you know for the concave surface that the center points of the curvature will in the left side of the V, right? So here the R is minus, and he will find he want to find the image position and the lateral magnification. So for this one, okay. So we include we add the second surface, then the rule should be the first image from the first surface will become the object of the second surface. So the image of the first surface is here. And this one will be the image of the second surface. But this image is behind the surface in the right side of the surface. So it will become the virtual object of the second surface. So why it will become the virtual object? Because it is in the right side of the surface. And actually, because you add the second surface here, then the light is not actually converge in this position. It converges in other position. Okay, so it will become a virtual object for the second surface. So now we can calculate using the same equation here. Okay, so the equation is n. Okay, so the N1 means the left side, the light is travel from the left side. So the N1 means the left side. Oh, sorry. Okay, so the N1 is the refract index of the left side, so it's here. So we must use the 1.33 for the new N1. Okay, and for the object distance, because it is a virtual object for the second surface, so this distance will be 30 centimeter. So it should be right as the minus 30. And for the second term is N2 divided by S1. N2 now is in the right side, refract index of the right side, so it must using the 1. Okay, and here would be the N2 minus N1 divided by R. And the R, now we also say this is the concave curvature, so the R will be the minus. So here we're using minus 5. Okay, so after this calculation, we can get that the S-plan sorry. Okay, we can get the final result is S-plan will be positive 9 centimeter. Positive 9 means this is a real image. And the 9 will be counted by the surface here. After this surface behind the surface of 9 centimeter and the real one, okay. And so And then we can calculate the lateral magnification using the same equation here. So we got the final one, we got the result is a 2 positive 2 divided by 5. This positive means the same direction relate to its object, the object here. Actually, the object is downward, so the positive means the same direction of that, so it is also downward. And the smaller than the object, 2 divided by 5. Okay. Okay, so we can use the equation, this example to calculate the scene length. What is the scene length? The scene length means that the distance between these two surfaces is near 0. So the length is very, very thin. So that we call it as a scene length. And we can also use equation in the formal slides. We can write both the equation here, the refracted equation. Okay, so the S1 means the first surface, the S2 means the second surface, and also we know that the connection is the image of the first surface will be the object of the second surface. So we know that the S2 will equal to T minus S1, S1 plane. Actually, you can see here, this is S2. X2 actually we can using this S1 plane minus the thickness. But you know that this S2 actually is minus the negative sign. So we using the T minus S1 plane. So we will get the right sign of the of this one. Okay, so because we want to calculate the scene length, so the thickness of the T we can neglect equal to 0. So we can get the S2, the object of the second surface will equal to the image of the first image, first surface, and you should know that we have the a negative sign here. So using this equation to replace to the upper one, then we finally can get this equation. Okay, and the S1 is the object distance for whole system, for whole scene length system, and the S2 plane is the final image for the scene length. Okay, so we can rewrite the equation to this one. Okay, and okay, for the equation is one, then we can find if there are parallel lines go through the scene length. That means as the object distance is infinity because the parallel light. Okay, and we know that the light will finally convergent to a point, and this point that we call it as the F, focal length. And actually this F is a S-plane. Or we say that the light emitted from the F, that it will become the parallel one. That means that this is the object distance, and this is the image distance. And now the image distance is infinity, and the S will become F. So we can, using this one or using this one, we can get that the relationship of this equation. F 1 divided by F will equal to this equation. So this equation that we called it as the Lensmaker equation, because for the Lensmaker, he just using this equation and he can design his lens. Okay, and in most of the case, the N1 is the outside refract index will be equal to 1 because put lens in the air. So the equation also can easily write as this one. So 1 divided by S plus 1 divided by S prime will equal to 1 divided by F. So we call this one is the thin lens equation. Thin lens equation. And all of the sign is the same with the former one we mentioned. For example, for the real object, the S is positive. For the virtual object, the X will be negative. And for the real image, the S prime will be positive. For the negative image, the S prime will be negative. And for the F, for the convergent lens will be positive. Divergent lens will be negative. Okay, all the equation is the same with the formal one. This L means that the material refract index of lens, and the M means that the refract index of the ambient, the environment material. Okay, so actually the lens is a convergent lens or the divergent lens. Actually is when you see the equation here, then we can know that F is positive or negative. It depends on the relationship of the lens and the material. So from here you can see if the refract index of lens larger than the material, then this will become the positive one. Okay, so that is a convergent lens. But for the same lens, if the L, if the NL is smaller than the NM, then here will be negative. The upper turn, this turn will be negative, so it will become a divergent lens. So here, this picture means here, for the lens, the NL larger than NM, it will become a divergent lens. Okay, but for the same figure of the lens, if the NM larger than NL, it will become a divergent one. Okay, so it also the same with this kind of the lens, the convergent lens. Okay, here shows that the convergent lens and the divergent lens, this means positive lens. Sometimes we will say the positive lens, and this is a negative lens. Okay, so all of left side are the convergent lens, and all of the right side is the divergent lens. So how do you know, how do you identify which the lens is the convergent lens or the divergent lens? Okay, so one method is to see that in the middle, the thickness of the middle side larger than the outer side, that should be a convergent lens. That should be convergent lens. And when the outer side is thickness larger than the middle side, then that will be the divergent length. But this if we don't want to use the finger to test the thickness, then we can using the watch because we know that if the wall or the object when you see through the convergent lens very close, then you will see a virtual image enlarged. So later we will see it. So in following chapter we will show that. Okay, so but for the negative or the divergent lens, and the walls or the object will become smaller. Will become smaller. So using the enlarged wall or smaller wall, that you also can tell which one is the convergent lens and which one is the divergent lens. Okay. So the class will be end here. Okay. Is there any problem on this? Next time we will start to show the ray diagram and how to calculate the image through the lens. Is there any problem?
Professor,
Yeah.
so the slide is in the portal.
Mm-hmm.
Oh,
Slide? Yes, in the portal. Yes.
okay, all right, thank you.
Yeah.
I have a question. So
Yes.
the RE the distance from the surface go to the center. Is that right?
Which surface? Which distance? You mean that the object distance
The
or
R,
the?
I mean the 1/r or something. Is the RE the distance from the surface to go to the center of the? Oh yeah, this R given. R given.
Yes.
Okay. No.
Yes. Okay. Any other question? If not, we will end our class today.
Okay. So,
Thank you.
All right, thank you,
See
Professor.
you next time. You're welcome. Bye bye.
Thank you,
the
Professor.
professor.
Yeah, you're welcome.